Hello and welcome to lecture 13. So today we're going to talk all about cardinality, so let's jump right in. So the cardinality of a set A, denoted by these bars around A, is the number of elements in A. So let's go through some examples. The cardinality of the set containing 1, 2, 3 is simply 3, since there are exactly 3 elements in this set. The cardinality of the set containing 1 is 1, because there's 1 element. The cardinality of the null set, well, that's going to be 0 because there's nothing in there. And the cardinality of Z, what would that be? Well, infinity. We're going to quantize this a little bit later, but for now we'll say that it has an infinite number of things in that set. Now let's talk about a theorem. If A and B are sets such that the cardinality of A and the cardinality of B are finite numbers, then the cardinality of the Cartesian product of A with B is simply the product of the cardinalities of A and B. So let's give a proof for this. So the elements of A cross B are going to be ordered pairs of the form A comma B, where A comes from A and B comes from B. So now how can I count all of the elements in this set? Well, since there are A choices for A, and there's the cardinality of B choices for B, the total possible choices that I have for the ordered pair A comma B will simply be the cardinality of A times the cardinality of B. So this proof is a combinatorics proof, and we will see more proofs like this in the second half of the class when we discuss combinatorics and finite probability. So now let's look at one more theorem. For any set X with cardinality n, the power set of X has cardinality 2 to the n. So we will prove this later when we get into combinatorics, but it is a useful fact to know. Now let's introduce a new axiom. So the Pidgeonhole Principle. If we put n items into m containers with n greater than m, then at least one container will contain more than one item. So this seems pretty reasonable, right? Like common sense says that this should be true. But like anything in math, we either need to prove it's true or take it as an axiom. So for this course, we're going to take this as an axiom. But note that this does not need to be taken as an axiom. We're just doing it for this course. Now, there is a classical picture that goes along with the Pigeonhole Principle. Namely, I have a collection of boxes, and I have more pigeons than I have boxes. And if I try to put the pigeons into the box, very clearly, one of the boxes will contain 2 pigeons. So in this case, you can see I have 9 squares and I have 10 pigeon cats. And very clearly, one of these boxes has to contain more than one pigeon cat. In this case, this box here has 2 pigeon cats who are very angry because they wanted their own box. Now, what is the Pigeonhole Principle good for? Well, it's very good for proving lots of different types of statements. For instance, to prove this theorem here that I'm getting ready to state, you really need the Pigeonhole Principle. So for sets x and y with finite cardinality and for a function mapping from x to y, if f is injective, then the cardinality of x is less than or equal to the cardinality of y. If f is surjective, then the cardinality of x is greater than or equal to the cardinality of y. And if f is bijective, then the cardinality of x and y are equal to each other. So like what we saw in the last lecture, once I prove these first 2 statements here, the statement for bijectivity follows immediately from the definition of bijectivity. So the hard work is just proving these first 2 points. So how can I prove these points? Well, let's give an idea of the proof. So for these first 2 bullet points, I use a proof by contradiction. So for, say, the first point, I would assume that f is injective and the cardinality of x is greater than the cardinality of y. So what am I going to contradict with that? Well, I'm going to use the Pigeonhole Principle to violate f being injective or surjective. So just to draw a picture real quick, let's talk to Mr. Paint. So here, this would be the classical picture that I would want to think of. So here, f is going to be an injective function, and the cardinality of x will be bigger than the cardinality of y. So I have this extra point here, 3 for x, 2 for y. So if f is injective, I can map this point to this point over here. That's not a problem. I can map this point to this point over here, but what do I do for the third point? Well, the Pigeonhole Principle tells me that since there's more pigeons, in this case elements of x, then there are boxes over here. At least one of the boxes here has to have more than one element of x associated with it. So explicitly, this third point here has to map to something because f is a function, and therefore it has to map to, say, this point here. But that violates f being injective. So that's the basic idea here. A similar argument works for surjectivity. Now, as I stated before, the third point follows from the first two. If it's bijective, it's both injective and surjective. Therefore, both of these inequalities hold at the same time. The only way that's possible is if they are exactly equal to each other. Okay, the third point above is very useful. It tells me kind of two very important ideas. One, for sets x and y with finite cardinality, if there is a bijection from x and y, then the cardinalities are equal. So this gives me a way of showing that two sets have the same number of things in them. I simply need to show that there is some bijection from the two sets. So I can often do that by finding a particular bijection. So there is an analogy that was taught to me when I first saw this that I find kind of useful. Imagine you are a cow farmer. So as a cow farmer, I want to let my cows go out to pasture, but I want to guarantee that I get all of my cows back when I go to bring them back from the pasture to another pasture. So now let's say I have a bunch of cows over here like this. So a natural question is, how do I keep track of the cows? What I can do is, as I let them go out to pasture, so as say Bessie over here goes out to pasture, I take Bessie's bow tie off, and as I let Bessie come out of the gate, I take off her bow tie and I store it right here. So now I can do the same process with, say, Gerald and Jeremy as well. And now my cows are out of pasture doing whatever calculators do. And I have these bow ties over here, one bow tie for exactly every cow. So as my cows come back in, I give them their bow tie. And at the end of this whole process, if I end up with no bow ties left, then I know for a fact that I got all of my cows. So explicitly, if there is a one-to-one correspondence with the bow ties that I took off the cows and the number of cows, then I have the exact same number of cows that I started with. That's the idea here. If there's a bijection between two sets, then they have to have the same number of things. So in the case where I have sets of finite cardinality, this is true because I can prove it. In the case where I have sets of, say, non-finite cardinality, I'm ultimately going to take this as the definition of two sets having the same number of elements. So in addition to this statement here, this third point of this theorem tells me one other thing. I know that an implication is true if and only if its contrapositive is true. Therefore, if the cardinality of x does not equal the cardinality of y, there does not exist a bijection from x to y. So the second point is useful for showing that bijections can't exist between two sets. Likewise, you can take the contrapositive of these first 2 points here and use that to show that an injection or a surjection does not exist. So if you're watching this before you're doing your homework, you can use this for problem 6, I believe. But I gave you problem 6 before explicitly mentioning this out, so you'd have to kind of struggle with the idea to figure it out on your own. And again, the above theorem is going to hold for sets of infinitely many elements. We're just going to take it as the definition. Okay, so now that we have this idea of cardinality, let's be a little bit more precise in what I mean by something being a finite set. So previously I talked about sets with finite cardinality. That's a little bit of an awkward wording, so let's define finite sets. So for any n and n, we define n sub n to be the set of all of the natural numbers from 1 to n. A set S that is not the null set is called finite if there exists some n and n such that there's a bijection f from S to n. Secondly, if f is not finite, then we say that it is infinite. So what's the basic idea here? Well, the basic idea is that if there is a bijection from S to n sub n, then we know that the cardinality of S is equal to the cardinality of n sub n, which by definition, we can just count them up, is equal to n. Otherwise, if this is not true, if there is no such bijection, then we can't assign a finite value to the cardinality of S, therefore it has to be infinite. There has to be an infinite number of things in it. So let's give an example here. So the set A that contains the elements A, B, and C is finite because there is a bijection between A and N3. Explicitly, I can map A to 1, B to 2, C to 3, and it's pretty trivial to see that that's a bijection. Further, the set A, which is the set of cats and lawyers, is also going to be finite because there's a bijection between A and N2, namely I could say cats go to 1 and lawyers go to 2. Okay, so now let's give a new theorem. If there exists an injection f from S to n sub n for some n and n, where S is not the null set, then S will be finite. So what's the difference between claim 23 and the definition over here? Well, in the definition, I said there's a bijection, but here I'm saying that there's just an injection. So claim 23 is weaker than the definition, and in practice, claim 23 can be quite useful because it allows me to deal with injections rather than bijections. So explicitly, I don't have to show that F is also a surjection. Just a little bit less algebra to do, if you will. Okay, so how am I going to prove this? Well, if there exists an injection F from S to N, then I need to show that that implies that there's also a bijection, say G, from say S to X sub N sub M, where M is something that could potentially be smaller than N. So let's look at the basic idea of a proof in a picture form. So here, consider some set S, and I'm going to draw it to be a finite set, and then consider some set over here, N sub N. So all I know is that there exists a injection from S to N sub N. I don't actually know what it looks like. So for instance, my function f could map this point over here to 2. It could map this point to 3, this point to 4, and that point to 7. This could be my injection. Clearly, as I've written this function won't be a bijection from S to N sub N because it's not surjective. Explicitly, 1, 3, or 1, 5, and 6 don't have anything that maps to them. Further, if I throw away the points 1, 5, and 6 to make this a bijection, it's not a bijection from S to N sub M for some finite value of M because nothing maps to 1. So in order to build a bijection, I need to move things around. So explicitly, I can do the following. I can start counting from the first element here going up and notice, hey, nothing maps to 1, but something does map to 2. So let's take the thing that maps to 2 and instead build a new function G that's going to map it to 1. So now I can continue, okay? 1's mapped to. 2 doesn't have anything that maps to it anymore because I just remapped it to 1. 3 has something that maps to it, okay? Well, let's remap this down to 2. It's the first number that G doesn't map anything to. So I can remap this to here. So now I can continue. 4 has something that maps to it, so let's remap that to 3. 5 doesn't, so I don't have anything to do. 6 doesn't, so I don't have anything to do. 7 does, so I'm going to remap this element that maps to 7 to 4. Now, I'm out of elements of S. There's nothing else that S maps to. Therefore, I can now take this set here to be my N sub M, and I can notice that just from this picture, it's pretty obvious that G is a bijection. So, to be explicit here, if the blue lines represent a bijection from S to N sub M, where M is the maximum over all S's in S of the function G of S. So explicitly in this case, M is equal to 4. Now, this is the basic idea of the proof. See the text for a closed form of this function and a more formal treatment of doing this. So the formality of writing this function in closed form can get a little bit ugly because you have to encode two things. First, the element in S that maps to the smallest element in N sub N needs to map to 1, and then every other element after that needs to map to the next integer. So explicitly here, the 2 needed to map to a 1, and everything after that maps to either 2, 3, 4, the smallest natural number that I have not mapped to yet. But with this intuition and this picture in mind, the formal proof for claim 23 in the text, which you should read, should be pretty straightforward to follow. So now on to another claim. N is infinite. So how would I prove this? Well, if I go back to my definition, if a set is not finite, then it is infinite. Thus, I need to show that there is no bijection f from S to N sub N for any value n and n. So thus, I need to disprove the statement, there is a bijection from n to n of little n. So if I want to disprove a statement like that, I really don't have much to work with by just starting with an arbitrary function and trying to show that it's not bijective. That's a very hard problem. Thus, a good proof method is a proof by contradiction. So the idea of the proof is that if n is finite, then there's going to be a bijection between n and n sub little n for some n and n. And you can note that this is not possible by using properties of n. So let's graphically see what this idea of the proof is really saying. So here I have n sub n, just 1 through n, and here I have my friend n. Now if I have any injection from n sub n to n, I can do that trick that I did previously to rewrite a new injection f that maps, say, 1 to 1, 2 to 2, all the way up to n to n. So that's possible by the same construction argument that I did previously. So now I can notice that n has this element n plus 1 that does not have anything that maps to it. So explicitly, there is nothing to map to n plus 1. Now this is a problem because since nothing maps to n plus 1, this function f cannot be a surjection, which means that any function f from little n sub n to n cannot be a bijection. So let's now give a formal proof. And actually, before I jump to the formal proof, I forgot to mention this before. Back here in this definition, when I say that there's a bijection from s to n, this also implies that there's a bijection from n sub n to s, since the inverse of a bijection is a bijection. So here when I'm talking about the lack of a bijection from this n sub n to n, that's equivalent to talking about the lack of a bijection from n to n sub n. It's just sometimes more convenient to work with n sub n as the domain. Okay, so this said, let's look at the formal proof. Assume for the sake of contradiction that the set of all natural numbers is finite. This means that there is an n in n such that there is a bijection from n sub n to n, or equivalently, again, from n to n sub n. Now, since n sub n is finite, so just a brief discussion here, I know n sub n is finite since the identity map is a bijection from n sub n to n sub n. But I digress. Since n sub n is finite, there is some m in n such that m is going to be greater than or equal to f of x for all x in n sub n. So what does this statement really say? Well, my function f maps from n sub n to capital N. And since n sub n is a finite set, this function f is going to map to a finite number of values in n. And now since I have a finite collection of numbers in n, I can simply pick the maximum of that, and that will be a bound for all of the values of f of x for all x in n. So explicitly, I can take m to be the maximum of all x in n of f of x. We know that the maximum of a finite set of numbers exists, so m exists. Now that we have this bound for m, let's do something with it. M is an element of n, right? So since m is an element of n, so is m plus 1. That comes directly from the definition of natural numbers, if you will, or we just know this is a fact of natural numbers. So what does this tell me? Well, since f is a bijection, and since m plus 1 is an element of n, there has to be something in n sub n that maps to m plus 1. So explicitly, there must be an x in n sub m such that f of x is equal to m plus 1. But we also know that m plus 1 is greater than m. So now I have the statement that f of x is greater than m for this x in n sub n, and also at the same time, for all x in n sub n, m is greater than or equal to f of x. This is a contradiction. Therefore, my assumption that n was finite is false, and therefore n must be infinite. So you can notice here, this is actually also a proof that there is no greatest natural number. Now for an alternative proof, see the text. In the alternative proof, instead of using a bijection from n sub n to n, they build the bijection from n to n sub n. But again, since we're talking about bijections, you can freely swap the codomain and the domain, and the result still holds. Now let's talk about another statement. If f is an infinite set and S is a subset of T, then T is an infinite set. So a good exercise, which I'm actually putting on your extra practice problems for week 5, is to prove this by showing the contrapositive is true. So why would we want to do the contrapositive? Well, if I'm talking about something being an infinite set, then I'm talking about the lack of a bijection. So by taking the contrapositive, I now deal with finite sets, and since I'm now talking about finite sets when considering the contrapositive, I now have a function that exists, namely a bijection, that I can do something with. Okay, so this theorem tells me some things. The sets Z, Q, and R all have the natural numbers as a subset. And since the natural numbers are infinite, that means all of these are infinite. So explicitly, this statement here. So now I have a whole class of infinite sets. Let's talk about infinity a little bit. So a set S that's not the null set is called countably infinite if there is a bijection from S to N. Note that here it's not sufficient to simply be a injection. You actually have to be a bijection to be countably infinite. If a non-empty set S is either finite or countably infinite, we say that it is countable. Next, if a non-empty set is not countable, then we say it is uncountable or uncountably infinite. So there's kind of a natural question. Are there such sets? Well, I'll leave that as an unanswered question for now, and we'll talk about it later. So now a theorem, claim 25. For a non-empty set S, if there exists an injection F from S to N, then S is countable. So we really need to consider two cases. Explicitly, if F is countable, then one of two things is true. It's either finite or countably infinite. So those are the two kind of cases we need to consider here. So let's end this lecture with the idea of this proof. If there's an injection from S to a finite subset N sub N of N, then by claim 23, S is finite. Recall that it's sufficient to have an injection for the set to be finite. Further, if this is not the case, then I can use that injection to build a bijection from S to N. So how do I build that bijection? Well, this is the idea that I've introduced once before and referred to it for a different proof. I simply do this process here where I take the smallest element, map it to 1, and then in short order just keep mapping to the next integer. But for this case, since I'm dealing with all of n instead of n sub n, I keep repeating this process indefinitely. So that's the idea of the proof. For a formal proof, which isn't really that much more formal than this, see the text. Now we have some assigned reading. So I want you to read pages 46 through 47. In particular, I want you to read the proofs for claim 23, the proof for claim 24, and the proof for claim 25. So in this lecture, I outlined the basic idea for the proof for claim 23 and 25. So keep that in mind when you read those proofs. And for the proof of claim 24, the text does the same basic idea as my proof, but they explicitly prove that there exists a bijection from n to n sub n. So essentially, they're working with the function that is the inverse of the function that I used. Okay, so here's your meme for the day. Never discuss infinity with a mathematician. They can go on about it forever. And our next lecture is all about infinity.